more of that. Okay. So here we go. So that is not. Oh wait. Point. Oh, I guess that is. Okay, that's a unit circle. What does a unit circle mean? When I say that phrase, unit circle, what does that mean? Unit circle. Unit means one. You catching me? So when I say unit circle, what I'm really saying is one circle. So what do I mean one circle? How's that a one circle? Where's the one? The radius. The radius from the center to the edge, the length of that, for anywhere, from there to there, there to there, they're all one, right? The radius of that circle is one. So we talk a lot about the unit circle, and that's another way. So I hope I can make this real clear today. There's two ways you can define the trig functions. There's two ways. You know, the whole SOHCAHTOA thing, you know? Like, how do you know what is the sine, what is the cosine, what is the tangent? Well, what they are is they're ratios in triangles, right? That's the SOHCAHTOA thing, right? Sine of any angle. So if that means if you have a triangle and you have some angle 30 degrees and it's a right triangle, right? And they say this is 1 and this is a half and this is square root of 3 over 2. Oops, kind of scribbly here. For example, then the sine of 30 degrees is opposite over a hypotenuse, right? It's the opposite over the hypotenuse. It's a half over 1, which is just a half. And the cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So that's one way to define what is sine, what is cosine, what is tangent. How do you get their values? Well, they're ratios in triangles, right? So somebody stops you on the street, you know. You're out walking, they go, you're taking one of your friends says, you're taking one of those college math classes, so what is the sine or the cosine? You know, well, that might happen. No, I'm just kidding. But they're ratios in triangles, right? That's what they are. Ratios in triangles. Ratios in triangles. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. In a right triangle, it's ratios in right triangles. Now, another way you can get the exact same answers. Another way, and by the way, we're just, you know, let me mention, yeah, maybe it'd be good to be philosophical, if I can be philosophical with you for just a second. And maybe I've already done this. Have I said, is math real? Did I do that? Did I do that? No? Is math real? So let me throw it out there. Is math real? Let me just help you with the answer. The answer is, well, let me ask you, let me help you this way. What if I said I saw math on the way to class today? I saw 3. There it was. I just saw 3. You'd go, what do you mean you saw 3, Mr. Herring? You saw 3 cars or 3 people? No, not 3 cars or people or 3 objects of any kind. I just saw 3. Right? Just math itself, just pure math. I saw 3. What do you mean? You saw like the number 3 written somewhere? No, didn't see the number 3 written anywhere. Didn't see 3 objects. I just saw pure 3. I'd be ready for the padded room, right? So math is not real, right? You can't taste it, touch it, or smell it. Pure math. Just math itself. It's just in our heads. We're just making it up. I'm not supposed to let that information out, right? We're just making it up. What are we doing here? Class is over, right? It's true. I'm not joking completely. I'm having fun with it, but it's true. Math is made up, but it's made up to describe things that are real, right? You understand that relationship? Threeness is a concept we made up to describe things in the real world that fit that, right? So if I saw 3 cars in a head-on collision in McKinley and Blackstone, I could come to class, hey guys, I saw 3 cars, they're head-to-head collided at Blackstone and McKinley. You know the concept of threeness. I know the concept of threeness. We can talk about things in the real world. So that's what math is. Math is made up to describe things that are real, right? Math is a language we just made up to describe things real. Think about sound for a minute. Now, why do we do that? Well, because it helps. It helps us live life. Think about sound. What if I'm getting old, so what if my hearing, well, no, my hearing's okay, my eyes are going, but my hearing is okay. What if your hearing starts to go, right? And you have a job in a factory, and that machine's kind of hurting your ears. You go to the doc checks you out and says, yep, no more being around that loud machinery. I'm going to write a note to your manager to your supervisor that he needs to put you somewhere not near that loud machinery. How's the doc going to do that? If we didn't make up numbers to describe sound. What numbers do we have to describe sound? What number system do we just make up to describe the loudness of sounds? Decibels. We made that up. Sounds don't, you don't go, how many decibels? That doesn't go, I was 27 decibels. We made that up. We described that, right, by the energy. It's actually energy density, whatever. I won't get into all that. It's physics. But sound is really energy in a volume. It's energy density. And we made up a system called decibels. Now, why do we do that? Well, because it's so helpful to live life. Because if the doc wanted to write a note to your supervisor that you can't be near machinery at 100 decibels or louder, how would he do it if we didn't make up the decibel system? He'd go, well, tell your supervisor you can't be around anything louder than this. And you go, wait, I think how long, one more time about this. You go, yeah, you got it. That's it. Tell the man and you memorize it all weekend and tell your supervisor on Monday. No, that would be dumb. So we made up a system called decibels, and then the machines are labeled with decibels, and on you go. So math is made up to describe things that are real, right? So sine and cosine and tangent, same thing. So I want to make sure you really get what sine, because now we're defining in two different ways, and that might seem near like, well, which one is it, Mr. Heron? Is it ratios in right triangles, or is it like things on a unit circle? It's neither, or it's both. It's made up. It's made up. Do you get it? But these made up things fit reality. So we go with them. But they're made up. Do you realize that? You see how those work? In other words, what if you think, well, why'd we make up sine, cosine, and tangent? Sine, cosine, we'll get to the graphs in a couple chapters, but what sine, cosine, and tangent do is go up and down, right? You probably have seen a sine curve, right? We'll get to those, up and down. Because there's all kinds of things in the real world we live in that go up and down, up and down. All kinds, the waves in the ocean, right? The moon goes around us and pulls the waves every day, tide in, tide out, tide in, tide out, right? So scientists want to describe that, predict that. What do? They use sine, cosine, tangent curve. They want to talk about anything with the planets. It's all, right, how do they know about the solar eclipse? It's all these kind of, anytime something goes up and down, up and down, up and down, what you do is you use one of the trig functions to model it. Because trig functions rise and fall, rise and fall. The alternating, I don't have to go to the moon and the beach. The alternating current coming out of the wall, the 120. AC, it means alternating current. It's a sine wave. It goes up and down. Batteries are DC, direct current. They're just steady. But the stuff coming out of the wall is up and down. So what do? What do power companies do? They use tangent, made up things to describe something in the real world that goes up and down, up and down. All right, does that make sense? So therefore we're saying, well, here's two ways you could make up them and they would fit the number up and down thing we want that will fit these things we use in the real world. So one way is you could say, well, they're like ratios in a right triangle. That's one way that works. Ratios in a right triangle. So, katoa. Another way, and here's the way for today, and this is really the one going to be used most frequently, is you could say, well, look, if you got a dot on a unit circle, and it's going roundy, roundy, roundy around that circle, anytime you stop, how far over the angle you're at right then, they're calling, what's the angle here, T? They're calling the angle T. I'm used to calling it theta, whatever you want to call it, it's just a name. Whatever angle you're at, T or theta or whatever, how far over you are we're going to say that's the cosine of that angle, and how far up is the sine. Your x coordinate is the cosine of the angle you're at, and the y coordinate is the sine of the angle you're at. That works the same exact way, and we'll give you all the same numbers, and will be useful for things in real life that go up and down. Because what does that dot do as it goes around? It goes up and down and back up. See what that dot does? It goes up and down, up and down, up and down as that dot moves around the circle. So we say, hey, we could just use a dot, and then that'll represent things that go up and down, up and down. So do ratios and right triangles. Either way, it makes things rise and fall, and so we can use them for real life things that rise and fall. All right, so that's it. So that's exactly what we do. We take a unit circle and we say, anytime you're on the unit circle and you're cruising around, when you stop, that angle you're at right there, call that theta, call that whatever, how far over you are, we're going to say that's the cosine. We're going to define that to be. So we just make it up. In other words, that's a way of math saying we made it up. We defined it to be. It wasn't a logical reason. We didn't have to do that. We just said this will fit what we're trying to create here. The cosine of the angle will be your x-coordinate, and the sine of the angle will be your y-coordinate. So you want to memorize that and know it cold. X-coordinate, anytime you're on the unit circle and you're cruising around, your x-coordinate is the cosine of the angle, your height is the sine of the angle. So, and then if you use that, I think I briefly showed you last time, it'll come out to the same answers. It's going to be the same result as SOHCAHTOA. Let me prove it real quick. Suppose I want to show you that this definition results in the same answers. So suppose you have some kind of spot, you're at some angle theta, and you're going to say, okay, I'm going to say how far over is the cosine, how far up is the sine. That's the same thing as SOHCAHTOA. How do we know? Well, if you make this a right angle here, how far over is your x, how far up is your y. And this is a unit circle, so the radius is 1. So look at that. If I said, no, SOHCAHTOA is SOH, so sine is opposite over hypotenuse, right? That's one way to do it. What's opposite over hypotenuse? Opposite over hypotenuse, y over 1. In other words, sine is y. And what am I saying sine is here? Y. Same thing. Do you see that? See how the y value on a unit circle is the same as the SO way of defining it? And same thing for the CA. If I did the CA for cosine, cosine is adjacent over hypotenuse. In this little triangle, adjacent would be x, right? X over 1. So cosine is x, which is exactly what I'm saying. Two ways to get to the same result. See that? Unit circle or SOHCAHTOA. Same result. Two ways to make up things rising and falling, rising and falling. All right. So with all that, I wanted to give you that background. I hope that makes sense and sets it on a real, like, you know, what is it we're doing here? That's what we're doing. We're making stuff up to fit things that are real. Okay, so now let's practice that making up stuff. Find the values of the trigonometric functions if the point is 15 17ths, 8 17ths. So they're saying this point, this P point right here, is over 15 17ths up 8 17ths. So in other words, what is 15 17ths then? If it's the x value, it's the what? That's the cosine of the angle, and here they're calling the angle T. And the y value, if it's the y value, it's the what? It's the sine of the angle you happen to be at. That's right. So you open to a certain angle and you shoot out to that point. Does that make sense? If you have the unit circle and you just say, I'm going to open to some angle, zoop, there's my angle, and I'm at whatever point I hit, the x coordinate, the y coordinate of that point, 15 17ths, 8 17ths. So they want the sine here. What's the sine? Part A, they want the sine. Yeah, it's the 8 17ths. Right, and then the next part, there's 5 parts remaining, if you can see that down there. Well, it's down there. Anyway, 5 parts remaining, so they're going to ask for the other 5 trig functions. So what's the cosine? We already said that's 15 17ths. How am I going to do the tangent? What am I going to do for tangent? Sine over cosine, right? Everybody good with that definition? You put all those, you get your 3 by 5 card in that exam. You know, have it ready for the practice exam on Wednesday. It'd be a good idea. Sine over cosine. So sine 8 17ths over cosine 15 17ths. Everybody with me? Everybody see that? Okay. And now, what do you do with a fraction over a fraction? Had this a couple times. Just get more comfortable. What do you do with a fraction over a fraction? Yeah, you flip it up, like the high diver flipping, like a fish flipping back out of the water there, upside down, times, see it flips upside down, right? Because dividing is upside down multiplying, right? 17ths cancel, 8 15ths. So the tangent is 8 15ths. We got the sine, we got the cosine. The other 3 trig functions are just the upside downs, right? That easy enough. Can I just do it real quick? Cosecant, upside down of sine, 17 eighths, right? Upside down. Cosine, the upside down is secant. So just flip it, 17 15ths. And cotan, upside down of tan, 15. That's a 15 over 8. And we got them. All 6 trig functions because x is cosine, y is sine. On the unit circle. And they said unit circle. Good on that? Questions on that one? Can I move on? All right. Okay. So they're asking for the sine of 11 pi over 6. So I don't know how you're doing on the radians thing, we're pretty new to it, so I'm assuming you're not that comfortable yet. That's fine. If you know right where that is already, then great, just grab it. I'm assuming it'd be more helpful to change to degrees. So I'm just going to plug in 180 for pi. That's what we always do, right? Pi is the same as 180. I'm going to change to degrees because basically I'm looking for which one of these dots is the angle 11 pi over 6. And once I got the dot, sine's just going to be the y-coordinate. So I'm just going to grab the y-coordinate. I just got to find which dot it is. You with me? That's my only job here. Oh, was I supposed to do roll? I don't like doing roll. Maybe I'll do roll in a little bit if we have time. 11 times 180. I just don't like using up time. 11 times 180 over 6. Everybody good? I'm just plugging in 180. Again, if you're comfortable with radius, you know right where that is already. You don't need to mess with this. 6 into 180, 30. Right? 6 goes in 18 3 times. 11 times 30. It's 330. Right? We don't need a calculator for all that, right? 6 goes in 18 3 times. And there's a 0, so 30. And then 30 times 11 is easy, because 3 times 11 is 33, add a 0 at the back. Right? So 11 pi over 6, 330 degrees. Which one of these dots, can you tell, is 330? Do you understand how the dot, let me help you, let me clarify the dots a little bit for you. Do you see what they're doing? This is 30 and 60, and then 90, of course, is straight up, right? See, they're going by every 30. See that? So this would be 120, 150, 180. They're doing all the 30 marks. See, they're skipping the 45s. Remember how when I showed you the unit circle, I also showed you the one right in the middle? What they're going to do is just show you the 30s, like they're going to have a bunch of them like this, and then at the end of the section, they put the 45s in there. They kind of separate them. I showed it to you all at once. Like right in the middle, there's also a 45. Halfway to 90, right? Straight in the middle. You with me? How we doing? You guys are giving me the poker face again. I don't know if to say keep talking more or less. Give me affirmation or whatever the other one is. Tell me that you don't understand. So right, so they're skipping the 45. That's okay. I mean, there's a bunch of angles we're not showing. But remember what we do is we memorize 3 angles, or put on your 3x5 card. We do without a calculator. 3 angles in every quadrant, right? Meaning these 3: 60, 45, 30. Right? The other ones we just use our calculator. Is that making sense? So remember when I give you the exam, practice exam on Wednesday, same thing on the real exam the following Wednesday. It's going to have whatever it is, 9, 10, I forget, questions in the first part that are no calculator. Right? Where you use your 3x5 card and it'll be angles like 30, 45, 60, or the same thing in the other quadrants. And you'll just do them without your calculator. And then part 2, I'll give you angles that are not 30, 45, 60, right? So anyway, so let's find out where this is. 210, 240, 270, 300, 330. Not 333, but 330. It's this one, huh? So what's the sign there? Negative 1/2. And we're not surprised it's negative, right? All students take calculus. Only cosine and his upside down, secant, are positive in that quadrant. So it makes sense the other 4, including sine, are negative. Good. And sine is also a y value, and the y value is down there. Of course it's negative. Good on that? You just find the spot, and that's all you got to do. Can I move on? Is that okay? So I just converted 11 pi over 6 to 330 degrees. These are going up by 30 every time. They're skipping the 45s. And I found 330. And this is the last section that is on our test. You guys are going to ace the test, right? Try that one. Try that one. So there, and here's the question. I should write the question here. Cosine pi. So I want the cosine of pi. Let me give you a second. Try that out. So put in 180 for pi, so it's cosine of 180 degrees. Where's 180? It's this dot right here, huh? We get what's the cosine of that one? Careful, it's this little right here. Clearly, that's the point back 1 up 0, isn't it? Remember, this is unit circle. So, it's only going out 1, right? It's a unit circle. So that point, can you see it? It's kind of small right there. Back 1, up 0. That's the coordinates of this point. So that's the x value and the y value. So cosine, is it x or y? It's x, back 1. The x value of that dot at 100, at this opening, which is 180 degrees. The x value is back 1, negative 1. Everybody good with that? So sine and cosine can be made up to be x and y values on the unit circle as the dot goes around, or it can be made up, it can be represented, modeled by SOHCAHTOA. Either way, it works the same. All right. Really comfortable in radians, but either way. So tangent, let me write it here for you. 5 pi over 3. Try that one. I'd probably convert to degrees unless you're super comfortable. Use your calculator if you need to. So find that angle. Feel free to check with those around you. Okay, so put in the 180. So actually, this kind of question you would be required to do. This could be on part 1, in other words. Can you do this without a calculator? You know, just make sure, 3 goes into 18 6 times. Throw the 0 on the end, right? Remember, numbers with zeros on the end, just do the math without the 0 and then throw the 0 back on when you're done, right? So 3 goes, you know what I mean? 3 goes into 18 6 times. Then throw the 0 back on, okay? And then it's a 5. My 5s don't look so good. 5 times 60. 5 again, just do the math without the 0. Just 5 times 6. Forget about the 0. 5 times 6 is 30. Throw the 0 back on. See what I'm saying? So you don't need a calculator. Okay, so tangent 300. That's what they're really asking. Tangent 300. So which angle is 300? Remember, this is 90. 180, 270, so right there must be 300, right? We good? Find that spot. So this is the dot we're talking about. Tangent. Now remember, tangent is sine over cosine, right? Sine is y value, cosine is x value. So y value, x value. So y value minus root 3 over 2 over x value a half. You know what you do? You flip that one up. Minus root 3 over 2 times 2 over 1 cancels, minus root 3. Is that good? Minus root 3. How many got that? Let me just see if I need to speed up or slow down. Okay, maybe 2/3 of you. Is there more I can say to help with that one? Not making sense what I did there, so convert to degrees, and then 270 is 300 y over x, because sine over cosine. And sine is always y, cosine is always x. All right. Yeah, yes. A question, yes. Or comment.
So y is only 1 or negative 1 when it's straight?
Yeah.
And it's exactly on one of the
Axis lines. Totally. Yeah. Yeah, good point. Good point. I haven't really talked much about that up to now, but you're right on. Yeah, like this point, this point, this point, and this point. Yeah, remember, they're just normal coordinates. It's nothing weird. So this is just the point over 0 up 1, isn't it? Just like from your algebra graphing, right? And this is back 1 up 0, and this is over 0 down 1, and this is over 1 up 0. Just normal x, y, and again, the x is always the cosine there, and the y is always the sine there. Right? At any dot on that unit circle, the x value of that dot is the cosine, the y value is the sine of the angle leading to that dot. Yeah, so for 90 degrees, which is the angle leading to this dot, the cosine of 90 would be 0, because it's the x value, and the sine of 90 would be 1, is what that's saying. You're right on the money. Good? All right. All right, so cosecant 5 pi over 6, try that one. So again, convert to degrees, unless you're super comfortable already in radians. All right. So put in a 180 for pi. We get cosecant of 5 times 180 over 6. 180 degrees over 6. Good so far? And then 6 goes into 180. 30 times, 5 times 30, this is 300 degrees again. So here's 270 straight down, right? Right? Oh yeah, what am I doing? I'm the math teacher here, but clearly I'm having some trouble, so. 3, 5, 3, 150, yeah. That was funny. All right, cosecant of 150 degrees. Thank you. It's not 300. So yeah. So where's 150? 90 is straight up, and this is 180. So and this is remember you just add 30 to each jump, right? So there's 90 straight up. Add 30. This is 120. This is 150. So that's the one. Right? You with me? So it's this dot right here. That's the 150. So it's these guys. Now cosecant is upside down of sine. Remember, he's the upside down of sine. So it's 1 over the y value. Because sine is the y value, right? So this is the x value, y value. So it's 1 over a half. Flip it. 2 over 1, 2. Good? On that? All is well. So on the part, so this stuff could be on part 1 on the real exam. I'm not going to give you this. I'm going to expect you to put that in your 3x5 card. So put that in your 3x5 card. I'll just ask you this. Good there? No questions I can answer? All right. Sine 3 pi over 2. Do that one. Okay, how we doing? 3 pi over 2, put in 180 for pi. You get sine of 3 times 180 over 2. Let's see if I can do it right this time. 2 into 180 90 times, and 3 times 90. I'm thinking that's 270, right? 270, where's 270? This is 90 straight up, 180 over here, 270 straight down. So it's this dot. It's right on the axis. That's why I want to do that. It's one of these right on the grid lines, right? 270 straight down. So it's this dot right here. What's his coordinates? Over 0, down 1, right? So that point, how do you get down to that point? You go over 0, down 1, don't you? To get to that dot right there. So that means the x is 0, the y is -1. What do we want? Sine. So we want the y coordinate. So we want the -1. Done. So you check it in your calculator. Hit sine of 270. It'll be -1. That's what we're doing. Is that good? Questions on that? So that's how we made up trig functions. SOHCAHTOA or unit circle, either way, they give the right values, which we use in the real world. Things go up. And this one, actually, this would be even a better one. All right, let's do this one. Try that one. You all finding that one? It's the same angle we had a second ago, right? Put the 180 in there for pi. So secant of 3 times 180 over 2. Like that. And then 2 goes into 180 90 times. 3 times 90, same spot. 270. Now where's 270? Straight down. We just did it. Right, there's 270. And so it's 0, 1. So it's 0, negative. Now secant, what is secant? 1 over cosine, right? Remember, he's the upside down one. You can have those in your 3x5 card. So secant's the upside down of cosine, right? You'll have that in your card. And so cosine is x, so it's 1 over the x value at 270, right? The x value. So it's 1 over 0. X value is 0. So what does that mean? 1 over 0. Good, undefined. Remember, that's craziness. We say undefined. Now you know I did that little spiel about mapping real stuff. Now I can make sense. When we say undefined, there we mean there's nothing in the real world that connects with having 0 in the bottom of a fraction. You can't do that, right? 0. The bottom number in a fraction is the number you cut it into. If I say I had 1/3 of the pie last night, that means the pie was cut into 3 pieces, right? And I had 1 of them. Well, then what does this mean? You can't cut a pie into 0 pieces. You can't do that in the real world. You might think, yeah, just don't cut it. No, it's 1 piece if you don't cut it. You can't cut something into 0 pieces. That's impossible. That's why we say undefined. That's why we say it's not just 0, it's undefined. We mean there's no connection in the real world. Right? So we don't like that. We don't let 0 in the bottom. There's no connection in the real world. That's what we mean by undefined. No definition in the real world. So undefined. That good? The answer is undefined there. Secant, and if you calculate, try it. Try any calculator. If you have secant, or I guess you'd have to do cosine and then flip it, you'll get air, or different calculators will say different things. Air, or something like that on that. Good? We good with that? All right, so here's the story. Sine and his upside down cosecant, they always go together with their reciprocal function, and tangent and his upside down cotangent are odd functions. And cosine and his upside down secant are even functions. Now, what do we mean by odd and even? We mean what happens with a negative. We mean like if you take the sine of some kind of negative 30 degrees or any other negative angle, you can just yank that negative to the front. Basically, I'm going to give you rules right now by which you'll never have to do negative angles if you don't want to. You can always just yank the negatives out of the angles. So what I'm saying is sine of a negative angle, you can just pull that negative to the front. That's what it means to be odd. It means you can pull negatives from inside the toaster, plugged into the function, the sine, cosine, no, not cosine, sine or cosecant, tangent or cotan. You can just pull it out. So say you got the tangent of, I don't know, negative 100 and, well, anything would work, but negative 150, oops, negative 150, for example, you can just yank that negative to the front, and then just do tan of regular 150 and then make the answer negative. Does that make sense? That's what an odd function does. An even function, if you have like the cosine of negative 150, because he's even, you know what the negative does? It just vanishes. Doesn't go anywhere. Gone. Poof, like a magic trick. That's what even does. So does that make sense? A good thing to put in your 3x5 card and to know is that cosine and secant are even functions, and the other 4 are odd functions. And what odd means is negatives inside you can yank to the front for sine, cosecant, tangent, and cotan. And cosine and secant, negatives inside you can just ignore. They just go away completely. It's an even function. Maybe if I have time, I'll show you why later. Like why do they do that? It's actually pretty easy to see on a graph why they do that. But let's just get used to it. I think that'd be better for you, is just to get used to doing it first. So what does that mean then about this question? Well, what that means is that because sine is odd, I can just grab this negative and just pull it to the front, huh? That's what they're saying. Use even an odd truth to do something nice with that negative. You don't have to. If you wanted to just find the sine of negative pi over 2, that would work too. But they're saying, hey, an easier way, if you don't want to have to mess with negative angles, you can just pull it to the front. So I'm going to do that. I'm going to say, well, this just equals negative the sine of pi over 2. I don't need to deal with negatives inside the parentheses if I don't want to. So what is pi over 2? Yeah, because pi is 180, as you know quite well, I'm sure. Pi is 180, so this is 180 over 2. Oops, getting scribbly here. This is 180 over 2, which is 90. So it's negative the sine of 90. So Okay, so let's find the sine of 90. It's negative, whatever the sine of 90 is. Where's 90? 90 is right here, straight up, 90 degrees. This dot right here, x coordinate, y coordinate, over 0, up 1. Sine is the y, negative y value there, negative 1. Right? Everybody good with that? Now, do you notice how it would have been the same answer if we would have left the negative inside? If I had done sine of negative 90, instead of pulling it to the front, just leave it. Where's negative 90? How do you do negative 80? You start here. This is 0. Straight over here is 0. Right? How do you do negative? Where's negative 90? You go down instead of up. Right? So you go down 90, which would be right there. Right? This is negative 90. It's also 270. If you're going forward, it's 270. If you're going negative, it's negative 90. Same spot. Right? You with me? This dot straight down is negative 90 or it's 270, whichever way you're going. Right? It's like a clock. There's two ways to get to that number on the dial. So it's negative 90 or it's 270. Anyway, so they're saying negative. So negative 90, which is over 0, down 1, that's the x coordinate. I'm showing you a second way. If we had just left the negative in there, that's okay too. So what is the sign there? It's the y coordinate. What's the y coordinate? Negative 1. Same answer. See that? So you can either yank the negative to the front if you just don't want to mess with negative angles, and then just find the sine of regular 90, which is positive 1, but then the negative's in the front makes that negative 1. Or you can leave it in there if you're okay with negative angles, and just find the sine of negative 90, which directly is negative 1. Either way, it's true. Make sense on that? That's what they mean by even odd functions. Questions? All right, so try that one. Sine and 9. Now, by the way, notice they changed the picture. They're just giving us the 45-degree spots. Right? They're not doing 30, 30, 30, 30. Right? You guys see what I'm saying there? So this is 45. They're just going halfway, aren't they? 90 just went halfway. And then so they just keep adding 45. This would be 135 because that's 90 plus 45. And then this is add 45. This is 180, as you know. Add 45. This is 225. Add 45, this is 270, as you know. Add 45, this is 315, and this is 0 or 360, either one. So see how they're changing the picture? I put both those pictures together for you. That's what you can do whatever you want. You can do two separate pictures. So those are that. And remember, I gave you those values. Remember my small, medium, large thing? Remember when I gave you the small? See how they're doing the same thing I did? Right? Remember when I gave you small, medium, large last week? Right? You guys haven't been able to think about anything else all weekend, right? Small, medium, large. All right. Remember it was root 1, root 2, root 3, all over 2. Remember that? And I said in the middle, right in the middle, you get the medium. Right? Because it's over medium up. See how those are the medium values? Root 2 over 2, root 2 over 2. See that? Whereas if you're here or here, which they're not showing on this picture, you get the small and large going together. Right? Look back here. Right? See this? This spot is over a lot, up a little. Over the large, up a little, etc. Right? So in this picture, with all the 30-degree angles, 30, 60, 90, 120, all the adding 30, they're giving you all the small and the large values, aren't they? See the half and the root 3 over 2? Right? Half is the same as root 1 over 2. Right? My small, medium, large. This is the same as a half, isn't it? So the small and the large, or the half and the root 3 over 2, they always go together at 30-degree increments. Do you see it? Right here at 30 degrees. It's over a lot, isn't it? Only up a little. See how it's over more than it's up? Whereas this one, he's only over a little, up a lot. Say over a little, up a lot. Right? Remember that? How I gave that to you the other day? That's all they're doing. That's all they're doing here. So they're giving you this picture that has all the small and large, 30-degree increments. And then they're giving you this one, which has the mediums everywhere, because they're always in the middle, 45-degree increments. So it's the same deal. So let's find the sine of 9 pi over 4. So stick in the 180. Give that a try. You're going to need to convert. It's going to be more than 360. So you'll need to, take out a 360. See if you can get that. I'm sure you can. How are we doing? So this would be the sine of 9 times 180 over 4. Can you do this out of the calculator? 4 goes into 180. Well, yeah, you cut it in half twice, right? Dividing something by 4 is, quartering something is cutting it in half twice, right? So cut 180 in half, it's 90. Cut it in half again, it's 45. You with me? That's 45. Right, 1/4 of, half of 180 is 90, half of 90 is 45. So it's 9 times 45. You can do that over here on this side. I'm going to do it without a calculator as well. 5 times 9, 45. 4 times 9, 36. 405. So it's 405 degrees. So it's the sine of 405 degrees. That's more than 360. So subtract a full circle. What do you got, 45? So really they're saying find the sine of 45, aren't they? They're saying do a full 360 and then 45 more. That's 405. So that's right here. What's the sine? The y coordinate, because both the x and the y are the same, doesn't really matter. It's medium, medium. There it is, root 2 over 2. We good on that one? With that picture, the odds were it was some kind of root 2 over 2. I guess it could have been a 0 or a 1. Good? No questions? Okay. So 10 sine of negative t minus sine t. All right, what's the rule here? Yeah, so with sine, I'm going to grab this negative and yank it to the front, huh? So you got a negative in a sine, yank it to the front, so it becomes negative 10 sine of regular t. Good so far? So remember when you put a negative in sine or his upside down or tangent in his upside down, you just yank them to the front. And now, okay, so what? Now what? What do we do with this? Yeah, exactly. They're saying let sine of t just be a. It's just like calling it a new name. Like, hey, I'm going to call that dog Rover. And we're just giving it a name. We're just saying, hey, sine of t, I'm going to call you by the name a now. That's all they're saying there. So this is minus 10a. Minus a. Just renaming. That's all we're doing. Like naming a pet. So now remember from algebra, what's minus 10a minus a? There's a 1 here, right? Negative 11a, huh? If you lose 10 a's and you lose another a, you lost 11 a's. There's the answer. That's all they want you to do. I don't know why they're doing the renaming thing, to tell you the truth. It seems a little weird to me. But, all right. I don't know why we couldn't have just said it's minus 11 sine t. That's the same thing. But whatever. That's fine. We'll do their renaming game. Good there? That makes sense on that? They're hitting on something a little different here. When 4 pi. That's 2 pi and 2 pi. How much is 2 pi? 3/6. It's a full circle, right? We good with that? 2 pi is a full circle. So basically they're saying, hey, add 2 full circles. So what happens if you add 2? If you're trying to find, if you're on the unit circle, you're like, I'm right here at some angle t, but then I'm going to go around 1 full circle and another full circle. I'm still at the same spot, aren't I? T plus 4 pi, 2 full circles later, is the same as t. It's the same spot on the unit circle, isn't it? You with me on that? Do you realize that the sine of t is going to be equal to the sine of t plus 4 pi? If you can read my scribble right in there. They're going to be equal, right? Because if you add you can add 360s, 2 pi's, all day long, and you're just going to come right back to where you were, right? So they're looking, do you know that's just sine of t? That's what they're saying. That's just sine of t, because we just added a couple full circles, which does nothing. You're at the same spot, whatever that spot originally was. We don't know, but it's the same thing. Next one, or it's minus, cosine. Now, what's that? Same thing. Whenever you take one of these trig functions and you start adding a bunch of 2 pi's, that's 2 pi 5 times, isn't it? That's 5 full circles. That does nothing. You're right. You're wherever you were, same spot. So you see what I'm doing? I'm just subtracting 360s, effectively. I'm subtracting 2 pi's, right? Yeah, maybe you should think I just subtracted 2 pi twice. I just subtracted 2 pi 5 times. Remember, we always know we can subtract full circles, and we're right back where we were. So far, so good? Now, here's the last. So that you know. That's not new. But here's a special fact I haven't said yet. With tangent, tangent doesn't just repeat itself after a full circle. He does. He repeats himself even more frequently than that. He repeats himself every 180, every pi. So for tangent, and of course his reciprocal, they always go together, cotan, you can subtract 180 or pi, and it is the same. Like that means his period, what we're really saying, if I use the official math lingo, is his period is pi radians, or 180 degrees. That for tangent. The tangent and the cotan period, meaning, well, what's the period? How long till it repeats, right? It's just the cycle of repetition. So in other words, tangent repeats himself every pi or 180, whereas the other trig functions, sine and his reciprocal, cosecant, and not tangent, cosine and his reciprocal, secant, their period is 2 pi or 360. Everybody see the difference there? There's a lot of little facts to know, huh? So I'm giving you a 3x5 card. You can write all this down in a 3x5 card. Especially today, I'm just dumping facts on you. So these 4 trig functions, sine and his upside down, cosine and his upside down, their period is 2 pi, meaning they repeat themselves every 360, or 2 pi. So I'm using that right here. I'm saying, look, if I just subtract 2 pi's, that's the same thing, because he just repeats himself. And same thing for cosine. I'm saying, look, he just repeats himself, so I'm just going to subtract 2 pi's. Get to this. Same thing. Same value. Didn't change it. And tangent, what am I going to do for tangent? I'm going to subtract the pi from him because he repeats himself more frequently. Tangent repeats himself every pi, even more frequently. Every half a circle, every 180, tangent repeats himself. That's his period. All right, so I get to here, and then I just put in the new names, right? A is sine, B is cosine, C is tangent. So A minus B plus C, done. Are we good there? Yeah.
What if there's like a number where there says tan t plus pi? What if there's like a number there, like a 3 or a 5 or something there?
Yeah, we.
Just leave it?
Yeah, they won't give us that on these kind of questions. Yeah, well, there's nothing we could do with it. Oh, what do you got? You got some?
Yeah, I have one just like that that says.
What number are you on?
Same number, 16.
So, okay, is it like a 3 pi?
Yeah.
Oh, yeah. Let me show you. I get what you mean.
Yeah, t plus 5 pi. So
Right, I get you. So yeah, so if they had tangent, good question, t plus, let's say 5 pi. So it's kind of like how this one had a 4 pi. So it really good. Everybody hear the question? Yeah, I'm glad, because it randomizes it for each of you guys on the homework. So that's helpful. If you're doing it, it's great, because sometimes you can see the good questions. So yeah, so remember, for sine, the answer is for sine and cosine, we can subtract 2 pi's, because that's the period for sine and cosine, right? For tangent, what can I subtract? 1 pi at a time. So I could just subtract 1 pi, 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 and they're all gone. So it's just back to tangent of t. Everybody see that? 5 pi would have been a problem for sine or cosine, because I can only take away 2 pi's at a time. But for tangent, you can take away 1 pi at a time. You can fine tune it, and the whole 5 pi is gone. Everybody see that difference? Just get them out of there, just like I got the 2 pi's out of there. So for sine and cosine, you subtract 2 pi's at a time, because they repeat themselves every 2 pi. Tangent repeats himself every pi. So you subtract those. We'll see that when we get to the graphs, and we'll start. Definitely use your calculator. I would use your calculator on something like this. So try that one. Crank that one out. How we doing? You guys getting this thing? Cosine t. That's just b. What about this 1,000 pi? It's just gone. That's just a bunch of 2 pi's. That's 500 2 pi's. That's 500 extra circles. Just get it out of there. What's this? It's gone as well. Yeah, really, you're just getting rid of all those, aren't you? They're just gone. Because they're all, this is a bunch of extra half circles, pi's, 177 half circles. Tangent repeats itself every half circle, every pi. Right? Remember, he's different than sine and cosine. And then right here, this is backwards negative, but who cares? It's backwards a bunch of full circles, a bunch of 2 pi's. It doesn't matter. So really, these are silly questions in the end. B plus B minus C minus C minus A. Right? You guys see what I'm doing? The cosines are B, sines are A, tangents are C, plus 5A. Right? We had B and B, 2B, minus C minus C, minus 2C, minus 1A plus 5A is plus 4A, isn't it? There we go. Is that good? All that extra, they're just all that extra circle stuff. Really, you could just cross those out. That's what they're going to do every time. They're going to eliminate. Is that okay? We happy? Yes, because I want to get to the graphs. We need to go there. It's valuable for us. So they give me this, blah, 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 blah. You don't even need to read all those words. All you need is that formula, sine of pi over 18t. Like that, good so far? I'm going to put parentheses. You don't have to, but just to be real clear with you, that's the plug-in. That's the holes in the toaster where you plug into the sine function, right? And then they're saying, look, when t is 63, find e. So just take your calculator and just put in 63 right there. You guys have your calculator? Pi over 18 times 63. Like that, just plug in 63 for t. Hit the buttons on the calculator. Is it radian mode or degree mode? Yeah, there's no degrees. There's no degree symbol, so that's radian mode, right? Oh, I got my calculator too. So let's do that. Let's make sure we're in radian mode. Make sure you're in radian mode. That's important. And it's the sine. Use your pi button. Where's my pi button? There it is. Pi divided by 18 times 63. Oh, I get negative 1. Did you get negative 1? How we doing? We good? Negative 1? So make sure you get negative, and then they just want you to do the next one. They're just going to have you plug in a bunch of values. There's nothing more fancy than that.
I got 10. I'll do on radian mode, right?
Yeah, radian mode. Yeah, I'm not sure. Well, yeah. Well, here, let me write the way it would do. Yeah, just type it in just like this on your calculator. Make sure it's typed in just like that. Grab me after. I'd be glad to help with calculators if you have any trouble. Problem is all the calculators are a little different, so I'll need to help you individually. But just come on up. Just take 10 seconds probably. We good with that? And then the rest is the same. Then they're going to ask you what's the period. Basically, what does period mean? How long till it starts repeating? When you start seeing some of the values repeat, you'll know that's the period. So I'm going to end it in that, and